Well, hello everybody, and nice to meet you. My name is Timothée Hoffreumon, in case you don't know me. So thanks, Satu, for having invited me to give my talk on quantum theory do not need complex numbers. So you can see it's a clickbait title. So yeah, I did my PhD with Atul in Brussels, but right now in Bratislava, Slovakia, as a postdoc student. And I did this work with Misha Woods, mostly when I was in Paris. And Misha Wood is right now in Lyon, in France. He's a PI. So I don't know if you've heard about this saying. Yes, so in a nutshell, my talk would be about this result you might have seen by Marc-Olivier Renou and many collaborators, among which a lot of big names in quantum information. So I'm pretty sure you've heard about these results. It was all over the news in 2021. And basically, you will see me rambling about it for the next 50 minutes. So here is the outline of my talk. To be fair to them, I'll be giving half of my talk to really, phrase their result in a fair fashion, I hope, and try to understand it before presenting the arguments that Misha and I have to oppose to this result. And then I'll go into our arguments. So first I'll model what they mean, what we mean, by real quantum theory, and then go into little issues you can have with real quantum theory. So let's start with the beginning. What's the content of this paper? So quantum theory based on real number can be experimentally falsified. So they start with quantum theory defined sets of postulates. So here are 4 postulates that are taken from their paper. I'm pretty sure you've all seen this postulate in one form or another at some point in your career. So this is typically how the postulates are phrased in the Nielsen and Schwang book, for example. So basically the first postulate tells you, well, a quantum theory, you have systems that are associated with Hilbert space, and their state is associated with the normalized vector of this Hilbert space. Second postulate is the measurement postulate. So basically you introduce PVM or POVMs depending on what you need. Third postulate is the Born rule. So how you link a state and a POVM or PVM effect to obtain a probability of seeing some outcome R. And the fourth postulate is how to combine subsystem into a global system. So here in this case, subsystem S and subsystem T into the global system ST. You may see that it's missing the fifth postulate, which we usually use as the dynamics, so introducing a Schrödinger equation or Dirac equation, whatever mechanics you want, because they don't really need it for the results, so don't worry about the fifth postulate. And so you may remark in this postulate that, as many students have asked, I mean, the Hilbert space is defined over the complex numbers, but why is it so? This is a long question. And in the late 90s and early 2000s, Gisin and other people in doing quantum information realized that when you do a CHSH experiment, for example, so when you violate a Bell inequality, you don't really need complex numbers or complex operator in your formalism. You only have, let's say, the Z and the X direction of your block sphere that are used. And so there's the question, well, if the only thing I can use to test my quantum theory is the Bell inequality, because these are the only thing that do not depend on quantum theory, that are independent of quantum theory, and if they don't need real numbers, can we rephrase quantum theory without real numbers? And this is the question, like, can we do quantum theory without using complex number? And so this is a very old problem, actually. Like Schrödinger himself hated the appearance of complex numbers in his equation, because he was doing wave mechanics, and in wave mechanics, of course, you have complex number when you use phasors and stuff, but you can always take the real part of your phasors to have like a cosine function, and then you're happy, you're back in the reals. But for the Schrödinger equation, it couldn't have a satisfactory way of getting rid of that. So, for example, he ended up in between his second and third paper, I think, finding a real Schrödinger equation, but the problem is there were like 4 components to his equation, so it was a bit like a Dirac equation without being direct equation. So Schrödinger was forced to admit that, you know, complex numbers were intrinsic to his equation, although he was super pissed about it. And in the next 100 years, people remain very puzzled about the presence of complex number. There were a lot of works about it. I must cite, so I put a string of citation, I'll put it at the end of the talk, but I must cite Stuckelberg in the 60s, did a lot of work about it. He basically developed a full quantum field theory over the reals. And basically he showed that everything you can do with complex, you can do with the reals. It's just a bit more cumbersome. And there is some issue when you try to encode the uncertainty principle. But, you know, that's not a big issue if you're just trying to do measurements and statistics. But then there was another argument in the more like quantum information revival in the 90s and 2000s, which was popularized by Wouters, which is the fact that, yeah, usually we use complex quantum theory because real quantum theory do not have local tomography. So here I'll do a small parenthesis about local tomography. So if you go to mixed state representation, then a mixed state will be a trace 1 positive operator acting on your Hilbert space. So in finite dimension, this means that rho is a matrix that in the complex case is a Hermitian matrix. And you know that a Hermitian matrix is specified by n squared real parameters. So it means that your state space, the span of all your states, is a n squared dimensional real subspace of your n squared dimensional complex space of matrices. If you do the same reasoning with the real case, so you now have a positive and trace 1 operator on a real Hilbert space, your matrix must be symmetric, in which case it only has n times n plus 1 divided by 2 real parameters. Therefore, your state space is of this size. But now this induces a problem because when you try to define composite systems, so in the C case, you define your composite system in 2 ways. Either you do it constructively, so you take like 2 states, rho A and sigma B, and you compose them with the Kronecker or tensor product, and you get something with n squared parameter times nb squared parameter. Or you can do it non-constructively, so you take a global Hilbert space and define a global state on it, and so you get na times nb squared parameters because it's a global thing. And these 2 way of doing coincide, but if you do it over the reals, it does not coincide anymore. You have that the global way of defining states have more parameters than the local way. So basically, if you take the span of all your pure tensor product of states, all states that are in a pure tensor product form, you have a smaller space than the span of anything defined as a trace 1 and positive matrix. So this has a big consequence, which is that certain non-product states are locally indistinguishable from product states, and this is what they mean by non-locally tomographic. There is no way to locally certify that you have a state rather than another. And the usual example of it is differentiating between 2-party preparing maximally mixed state and 2-party preparing correlated Y states. So Y, I mean the poly Y matrix. And so this is a real matrix, but it since it's only involve complex matrices that when they tensor together become real, the fact is when you try to do a measurement of this Y state, sorry, can you see my mouse actually? I'm not sure.
Yes, we see it.
Cool. Okay, so what I meant is, yes, so you have this state, but when you try to measure it with real operators, basically, since the Y matrices are complex matrices, they are orthogonal to the space of real matrices, and so you will never have non-zero interaction terms, and therefore the only thing that measurement can see is the identity matrix. So basically, this state is indistinguishable from this state over the reals. So you cannot say that this state is different from white noise. And so there is only by a global measurement you can certify that you don't have white noise, but this state. And this is a failure of local tomography, which was popularized by Wouters, but known way before him. And that's usually used against real quantum theory. But the problem is this argument is based on the dimension of the state space or the effect space or whatever. But the problem is that Brunner et al. In 2008 showed that you cannot test the dimension of Hilbert space. And so this is a bit terrible, because then you cannot prove that in a device-independent way your real quantum theory has a fixed dimension, and so you cannot distinguish it from a complex quantum theory. It means that there is no experimental evidence against real quantum theory so far. And so the result of Renou et al. Was basically to find one such result, so a difference between real quantum theory and complex quantum theory. And to do so, they first considered the Bell scenario, which...
Can I quickly interrupt you for a silly question? Right, so I guess it's probably just a matter of counting the dimension, but is the complex field the unique field for which this works? Like, for example, if you take quaternions or something else, is there like something special about?
Yes, it's actually very special, and there is a nice representation theory about it that I won't have time to talk about. But yeah, basically it's the fact that the dimension of the complex matrix scale as a square, and of course the square is distributive, whereas the real matrices won't be distributive, and the quaternions, it will be a different function, but it will be actually in the other way around. It will be over tomographic somehow. It will be, it's a very weird thing that happens with quaternions. And so you can show that basically every thing that is locally tomographic must have a power function as a function of the dimension. So basically you are forced to say it will be the complex of things similar to the complex in a certain matter, yes.
Right. But could it be that there's like some other notion of instead of requiring that the states are Hermitian, do you think there could be like some appropriate generalization or specialization of the notion that might make sense depending on the field?
Yes. So actually, you're kind of spoiling the talk. That's actually what Misha and I did, kind of. So basically, we redefined the tensor product to obtain something that actually scales the dimension correctly over the reals. So yeah, there is a way, but then it's very complicated. And I'll get to why there is problem with respect to the definitions and stuff.
Okay, thank you. So sorry for the intro.
It was a very good question. You're foreshadowing a bit what I'm going to say. So yes, so now talking about the results. So yes, so this has nothing to do with local tomography, just that local tomography could not be used. But to differentiate real quantum theory from complex quantum theory, Renou et al., then they wanted to find a non-local game, because non-local bounds are independent of quantum theory. But for a Bell scenario, so a bipartite state shared by Alice and Bob, and then Alice do some measurement E indexed by a setting X. So for example, if X equals 0, she measures along the Z direction, and if X equals 1, she measures along the X direction, for example. And then she gets outcome plus or minus 1. And then, so this is a P of EM element, and then Bob is doing the same with some F effects, depending on Y, and giving you an outcome B. So you obtain, I guess you all know in the Bell scenario, you obtain a bipartite distribution of 2 outcomes given 2 settings, and this is given by this function. And this, you can show that if you replace the states and the effects by a real matrix, there will be no difference. Any probability distribution you can achieve with complex quantum theory, you will achieve with real quantum theory. So there is no way to find a bound that won't be attained by one of the theory, but with the other. But this is no longer the case when you go to the entanglement swapping scenario. So basically, yes?
So just in the previous slide, do we have to increase the dimension to get the same condition, or is it?
Yes. So this is a good question again. This should hold for any possible dimension. So even if I'm representing correlation I can obtain with 2-dimensional complex system, I must try on every possible dimension of real system that I don't have the same statistics. So I can even go to infinite dimension real system to prove that I don't have an emulation or a simulation of the probability I can obtain with two-dimensional complex systems. So yes, this is important, and this is why you need the Brenner argument, is that no dimension can be fixed a priori, so you have to try in any dimension. There is another question.
Yeah, so I mean, I'm trying to understand, like, so I mean, I can think of, let's say, states are from some, cone, and then measurements are from the dual cone, and yeah, like, I mean, you take appropriate slices so that they are normalized, and what we really care about is the probabilities, right? So for
Yes.
that, what really matters is, like, I mean, the cone and the dual cone and the inner product between them is what gives you, like, the statistics. And the question of real or complex maybe is about what is the scalar that you use, using which you can scale the cone. Like, I mean, so we have this scalar, right? I mean, which we multiply with the element of the cone, and it has to remain in the cone, but you have to take appropriate slices, and also, I mean, so it's a question of the scalar, right? and and you are basically thinking about, like, composition of cones. If I think about, like, I mean, tensor product is one kind of composition, but I can compose cones in many different way, such that the composed cone and the corresponding, let's say, composed measurement give me, like, the correct statistics. Now in the world of cones, I mean, like, I mean, I can think of whatever way to compose, like, these different cones, right? I mean, like there is no as such restriction
No, I totally agree with what you're
coming from just
saying.
tensor product, right?
Yes. Once again, what I'm doing
Yeah.
here is explaining the content of the Renou et al. Paper, and basically the procedure you're describing is what I'm going to explain, and this is the content of our paper. So yeah, basically,
Okay, I see.
it's all about imposing the composition rule to be the tensor product. And here we'll be a bit more specific. It is still a tensor product of cones, but it's not the Kronecker product. So really, when you are in the representation of your cones, you should be using another bilinear form. We'll get to it.
Because I was thinking about you were talking about this local tomography, and then I was thinking, if, let's say, if that is the criteria, then, like, that is the, I mean, those kind of criteria is coming maybe from, at that statistics level, and for that, basically, what really matters is the interaction between the object and the dual object, and you have to compose objects such that when you take the statistics via the inner product defined on that appropriate space, like, the statistic has to be basically respected.
Yes. Right. Yes. So yes, exactly. So this we'll get into it. This is actually more subtle because the Renou et al. Result will show that you still live in some cones that are dual to each other, but they are not maximal. Like, you basically are restricting the cone implicitly, and this will be the very end of the talk. Yes. So, but the whole point is that the Renou et al. Paper is not at all a cone-like or GPT, if I may, presentation of quantum theory. It's really saying, like, this is quantum theory, this is non-local games. Let's find out what happens, and they never really talk about this cone structure, indeed. But we'll get to it eventually. So right now, what I was just saying is, so they don't find a difference in the Bell scenario, but then if they go to the bilocal scenario, which is basically entanglement swapping, so now there is Alice, Bob, and Charlie, and Alice and Bob are sharing a source, Bob and Charlie are sharing another source, and Bob is doing a global measurement on these two half of a source, and then Alice is measuring, Charlie is measuring. Only Alice and Charlie have settings, and then the three parties have outcomes. And so this is an entanglement swapping scenario, because if the source are Bell states and Bob is doing a Bell measurement, he just swaps the entanglement from he has in between the two parties to have entanglement between Alice and Charlie. And so what they found is that in this case, you have discrepancy. You have certain statistics that you cannot attain when. So you define your probability distribution as such, and then you say it's dependent on the field, and then if the field K is real, then all the matrices are positive real matrices, and if it's complex, they are all complex and positive matrices. And so what they show is that certain probability distribution you obtain with the complex are impossible to obtain with the real. In particular, you can build non-local games or non-local inequalities that rely on this probability distribution, and therefore there are non-local bounds you can attain with the complex matrices that you can never reach with the real matrices, even if, as you asked, even if you let the dimension of the real matrices go to infinity. And they actually find that the gap is quite large. It's the order of 25%. So the gap is so large between like what you can attain with real quantum theory and complex quantum theory that you could actually have enough visibility to test it in an experiment. And actually there were experiments trying to test it and reporting that indeed they found the bound predicted by complex quantum theory and not the one found by real quantum theory. So because they attained this bound, the paper claimed that they falsified real quantum theory. So this is a non-local bound, so it's independent of theory, and it showed that it attained the values of complex quantum theory. So it means that real quantum theory is somehow wrong. Okay, so now I'll do a bit more background and try to contextualize the result a bit. So the first title, of the paper was Quantum Physics Needs Complex Number. So now you understand the title of my talk. And the first thing it's important to notice is that this result do not at all tells you that quantum theory needs complex number somehow. And that's why they changed the title to Quantum Theory Based on Real Number Can Be Experimentally Falsified. It's because you assume you are in a Hilbert space quantum formalism that you transform into a real Hilbert space formalism. And this is only this really like restricted theoretical apparatus that you falsified. And so this is quite important because the problem of complex number in quantum theory is very old, but so is its solution. So there is another question. Yes.
Yes. Sorry to again, interrupt.
No, it's
I will restrict my questions. Yeah, number of So again, I'm trying to think of it again from the GPT, the cones language, cone language, basically. So basically, are they basically seeing in this cone language is that when you are composing different cones and taking scalars, which are, let's say, real numbers, then, based on experiments, a particular way to compose cones, let's say if we believe in that, and if we believe in, this source independence and other things, source independence and what else was it? I don't remember. So then you rule out the real scalars, but there can be other scalars that can be possible, and there can be other way to compose cones also, where you can allow real numbers if you violate that assumption that we are composing using that the tensor composition of cones.
Yes, basically that's it. Yes, you need to assume that. If you really want to think about it in terms of cones, you can think that they are basically going from the cones of Hermitian matrices. These are cones over the complex, to the cones of symmetric matrices, while keeping indeed all the scalars and the tensor product to be the same. And they ask how these things are different, and well, of course they are kind of different. Yes, but so
just a quick technical follow-up. So when you say cone, or you mean positive semi-definite matrices, I guess?
Yes. So that's usually sorry.
Yeah, okay. Just a small tech.
Yeah, positive semi-definite cone over some. It can be even like a convex cone, but positive semi-definite are a special kind of convex cone, and usually you generalize them into convex cone in all this GPT kind of language. Yes, and so here I was going to say, let's take a step back. Let's even forget that GPT is now the way of doing foundations, and before even that, there were other ways to do foundation, like the Hilbert space formalism. Everybody hated it at the beginning, And even von Neumann was very dissatisfied with it, and he created algebraic quantum theory to really like remove oneself from the Hilbert space, because here we are questioning whether we need imaginary numbers for Hilbert space, but we are not questioning even a more fundamental question, which is why do we need Hilbert space to begin with? This is a purely mathematical thing. This has no ground in reality. And so von Neumann developed, well, him among others, like Siegel or Jordan, developed an algebraic formulation in the 30s in which you now have C-star algebra, which are way more concrete as mathematical objects. I mean, they are very abstract, but how you define them through axioms is way more concrete, like you want convexity and this kind of stuff. And so there is this quote at the beginning of the first paper. They introduced the formalism of algebraic quantum theory and then quantum field theory, which is, well, we meet an old objection of quantum mechanics formalism, namely that it does not confine itself to the real domain. Complex numbers and the like are used here only as technical expedients. And what I mean by that is that there is real formulation of quantum theory, way of defining quantum theory without using Hilbert space. So here are the two oldest examples, which are quantum logic, that you may know, although it's kind of out of fashion right now, and algebraic quantum theory. And these two theories, which are nothing to do with the postulate, can be proven equivalent to the postulate through some representation theorems. And these representation theorems have the nice advantage that they work on several fields, among which there is the complex, which is usually the one we use because they are very easy to work with numbers, but you can also use the quaternion and the reals. And this is true for both theories and a lot of other theories like GPTs or, other formulation like GPTs or the convexity approach of Relevo and these kind of things. And yeah, here the message is that you could actually represent this very abstract definition of quantum theory over real Hilbert space. This is like the GNS construction. You can do it over the real, or you can use Solar theorem over the reals to represent quantum logic as Hilbert spaces. And so then if you know that, there is something weird about Renou et al. Result is that they basically are showing that these representations somehow should be not faithful, because somehow now when you switch the different representation, there is a discrepancy in the statistics. So this has made me raise some eyebrows, but I'll do now a quick summary before we go to the results I obtained with Misha. So we are asking the question like why the Hilbert space postulate of quantum theory relies on the complex field. We know that there are many arguments. I presented one which is, for example, local tomography. But there are many that I didn't have the time to present, but none of them has actually experimental prediction. And what Renou et al. Claim is that they found an experimental prediction of something that would differentiate between real quantum theory and complex quantum theory, which is very nice, but already like it's restricted the scope of the discussion to say it's not quantum theory that needs complex number, it's the Hilbert space formulation of quantum theory that needs complex number. So let's get to it now, and let's go into a bit of the mathematical details. So my first reaction was like, of course, this result should hold. The postulates are not independent of each other. If you change the state space postulates, you need to change the postulates of combination. Otherwise, well, you change something without changing something affected by it. Of course, it will change the whole dynamics. What I mean is that in the first postulate, you define a Hilbert space. In the fourth postulate, you define the tensor product of the Hilbert space. But a Hilbert space is defined over a field K, and the tensor product is a bilinear form of this field K. So if you change the field in postulate 1 without changing the field in postulate 4, of course, something weird happened. And so that's basically what I explained to Armin Tavakoli when he presented the results to my group in Brussels in 2022. I was basically sitting saying like, yeah, of course it will be true. I mean, I can use p-adic numbers, I can use quaternion, your result will be true in any other field than the complex numbers. They just say yes. So yeah, that's it. That was the talk. No, I mean, and so, okay, let's let's admit it. And so I continue. Yeah.
Sorry, I have a sort of silly question again. So I was wondering, could it be that if you go to quaternions and restrict the Hilbert space structure and preserve the tensor product as it is in standard quantum mechanics, using the Kronecker thing that you were saying, could it be that the quaternions are not able to produce some correlations that complex field can?
Normally, yes. There is no proof, but by the same reasoning, there must be discrepancy. But actually, since the quaternion have more degrees of freedom,
they're more expressive. Yeah, that's why I'm saying it could be very curious, right? Like you could say, like your argument is kind of pointless because look here, instead of restricting the field, we made the field more permissive, and yet your complex one is the one that's producing more correlations. Do you think that would be?
But the problem is the quaternions are not really a field, and then you arrive to another big problem with quaternion, which is that they are non-commutative. So defining the tensor product becomes very tricky. And there was actually a whole feud about it in the 90s because quaternionic quantum theory became very popular back then. And I think it's Perez who showed that you can have superluminal signaling with quaternionic quantum theory. But this is because basically your number field is no longer commutative. And you're just using the fact that two scalars do no longer commute with each other to signal.
Got it. So, is there any other field, any other candidate field, which is more general than complex that you could use, which is commutative?
Yeah. So there are a few results. There is a Russian guy, I forgot his name, that is working a lot with p-adic numbers to do quantum theory. It's super interesting, but like quaternions, it leads to obscure mathematical problems. So you could. And also, you could use spin factors, as Van Neumann showed. So spin factor, you basically impose some kind of super selection rule, depending on some Clifford algebra on your space, and this would work as well. And actually, like all this case has been treated in a source that I will cite in a future slide, which is the threefold way by Freeman-Dyson. Like there is a very old work in the 60s about treating all these cases in a very abstract way. We'll get to it. No, it's a good question. Actually, you've been very reactive, which is nice. I mean, I'm way behind schedule, but at least people are asking a lot of questions. So getting back to the presentation. So let's admit the result, and so that result can be phrased as the following. You have Hilbert space postulates, which use several abstract notions like a Hilbert space, validity of state, inner product, tensor product, which are non-specified a priori. Then we know that when we do mixed state quantum theory, for example, over the complex, all these abstract things are then represented in terms of if we are doing finite dimension matrices, otherwise it would be operators. So a Hilbert space will be the Hilbert space of complex matrix, or validity of state will be that all matrices are positive operators with trace one, inner product becomes the Frobenius product, and especially the tensor product becomes the Kronecker product, which is the usual matrix operation you do where you take the first entry of the left side matrix and you multiply it by the whole right side matrix, then take the second, etc., to form a new matrix. And so the real quantum theory that Renou et al. Had in mind in their paper is to basically take this representation and change every occurrence of the complex into real. So you have real matrices, real blah blah. So it just changed the Frobenius, but it also changes the Kronecker. And of course, you could do it with quaternion, but here the definition of a quaternionic Kronecker product is already skewed or problematic. So
I have a question on the complementary side too. So let's say instead of playing with the field, let's say because if let's say local tomography is my sacrosanct object that I should not touch, then I have also freedom with respect to the different ways I would like to combine these objects. So for example, you can combine using, let's say, this Kronecker product, or some other product or something. But so my question is, have people explored, has there been a study where, there are different kind of ways to compose these objects such that the local tomography is preserved? And then we can say that, see, you can keep, so there are two tunings. So one way to you can tune the knob of the field, and you can tune the knob of the product. And then, in some of them, I'm saying that, sure, like tensor product and real cannot give you something which is tensor product, like Kronecker product and complex can give. And
Yes.
and so on. And there can be some kind of a hierarchy between, some partial order or something. I don't know. Yeah.
So no, I see what you mean, and this is actually the case, yes. But on the one hand, these kind of arguments are usually trivial because there is this property of the tensor product, which is like it's a universal property. So you can do a bit of categorical nonsense to prove that basically in most cases all the possible variation of the Kronecker product will be isometrically equivalent to the Kronecker product. But indeed, and this is kind of what underlies our result, is that over a certain field, like the reals, it is no longer the case. Like you can twist a bit, indeed, the thing around so that you can find non-equivalent representation of the tensor products that are the non-equivalent representation of the tensor products from the Kronecker, sorry. But there is also a thing, to be fair to the Renou et al. Paper, is that they absolutely don't want to assume local tomography. They don't say that this must be a property that quantum theory should have. So you should be, these are very interesting as argument, but this is not totally related to what they are doing, or at least at first I asked them the same question, like, you don't have local tomography, what's the issue? And they basically
don't have local tomography. I see. Okay.
Yeah. So if you do this real quantum theory like that, it doesn't have local tomography, but they say it's totally fine because there is no testable thing in nature that can prove me that whether or not local tomography is a property that every system has. So that they don't assume it by fiat.
The local tomography example is the one that you gave, right, with identity and why is it?
Yes, this is this example. And so basically here they define their real quantum theory, how it's defined, it's non-locally tomographic, but they say it's fine because it's not really a property that we can test in any way, so why not just give it up? What I meant by this slide is just that real quantum theory, as it's defined, is just an analogy of representation from the representation we usually use. And so I went with that in a workshop, and I worked with Eva Borso, Carlo Marconi, and Diana Taschetto about it. And well, basically our first observation was that the Kronecker product, if you change the field, it becomes a totally different object. Like it's formally the same, but the mathematical objects, the abstract mathematical object it represents are totally different. And also it's quite easy to see that if you want to have a map that maps the Kronecker product to the real Kronecker product, so a map from the complex to the real that preserve all probabilities and preserve all Kronecker products, so something that is a monoidal functor, if I can use a categorical language, then it's quite trivial to see that this map cannot exist. You just have to input some number times I and times I the other side, and then just moving the i's around because you are allowed to move it around complex Kronecker product. You won't have the same result because you cannot move it around anymore since it's a real Kronecker product. So then,
can you say a bit more about the first point? I didn't understand like what you mean by abstract, like being different objects. Like, is it easy to understand or?
No, it will be a bit hard. We'll need to be to do differential geometry. But yeah, I have a slide that gets back a bit to it, so I'll talk about it a bit more then. But then, with respect to that, what we can say is that since there is no linear mapping from C to R, this is quite trivial to see. What the Renou et al. Results show that there is no mapping at all. Like there is no way to embed a complex quantum theory in a real quantum theory that always exists. But it doesn't mean that there is no way at all. And as we already mentioned, like this relies on the fact that you assume that you have Kronecker product on both sides of the mapping, but what about other representation of the tensor product? And this is the first paper. So I met Misha Wood in a conference who was also working on that. And we start sharing ideas, and he had a simple approach to the problem, which is let's just accept the postulate, find a model that is compatible with the postulate, and see what we must change. And so we call that representation locality. So these are basically the property I just showed you. So you want to keep, actually, this is a better slide to show what we mean by representation locality. So instead of calling it real quantum theory, we'll now call it real number quantum theory to differentiate. So that's the idea we have of a real number quantum theory. So it's a theory that, on the one hand, obey the abstract Hilbert space postulate, and on the other hand is representation local, which means that there is always a way to embed a complex quantum theory into a real quantum theory. So there should be a pair of maps that send all probability distributions, so in a product between a state and an effect of the complex theory to the state and effect of the real theory, that respects the composition rule. And in particular here, I don't have to assume, because we show that it couldn't be the Kronecker of our product, the real Kronecker product, sorry, it should be another bilinear form. We call here R product, the small r product. Okay, and so then we worked out basically a simple. Sorry.
So just to a question about notation. So gamma star is the complex conjugate? No.
No,
what is gamma star? Is it related to gamma or?
It's the dual. The adjoint. It's the
adjoint.
Yeah, it just so that it guarantees that if you take the adjoint back, gamma will cancel itself, and you guarantee that all probabilities are conserved.
But the gamma is a map from where to where?
So gamma is, and that's where it's not yet very well defined. But right now it's just a map from complex matrices to real matrices, a general map. But if we were to be a bit more precise, here gamma would be a map from the set of all states to the set of all states, and gamma dual will be the set of all effects to the set of all effects. And then the dual here is no longer the self-adjoint, but it's really the algebraic dual.
Nice. Yes.
Yeah.
So I cannot think of it as like just a transpose if it's just real.
Yeah.
It's like something entirely different.
Yeah, it could be the transpose, it could be equivalent to gamma, but here it just means some notion of duality that is yet to be defined depending on the representation and stuff. So yeah.
Sorry for the dumb question.
No, it's good to ask. So really, just to say that this one, when it has a little star, it sends an effect to an effect, and when it doesn't have a little star, it sends a state to a state, and then you try to define it around it, define the gamma map around it. And so we use the simplest representation we could find, which is any complex scalar become a 2x2 real matrix. So you transform every real units, so the number 1 into the 2x2 identity matrix, and you transform any number complex unit, so the I number, into this J matrix. So this is a very standard way of mapping complex to reals. And with this, we could prove quite quickly-ish that actually you can find a real number quantum theory by either doing two things. Either you drop the positivity condition and you weaken it into something else, or you drop, indeed, keeping the Kronecker product, drop it by some other linear form that is it is way more complicated and cumbersome to use, but it has all the property of a tensor product. So this is to say that compared to the theory that I have in Renou et al., we have two theories. One is positive and pure tensor, as I will call it, because, yeah, I don't have time to go into the detail, but it's just something where we weaken the notion of positivity. But this theory is very well ill-defined because it depends on how exactly the Hilbert space are divided into subparts. So this one is not the best. But there is another one, which is just to consider.
Can I ask, is this POPT positive on
Pure tensor.
product test by pure tensor. But then I believe there was some result by Asin and all, right? I mean, where they showed a separation in the tripartite case between quantum theory and a theory which is POPT.
Yeah, they are quite separate indeed.
I mean, Harry Berman and others for two-partite case, the bipartite case, like they showed that it's same correlation, but the moment you go for the tripartite case, I think there's a separation, right?
Yes, yeah, there is a separation. I think even in the bipartite there is. I'm not sure. I don't.
In bipartite they are same.
Okay. Yes, but here the important thing is that we are over the real. So I mean, it's normal there is a separation.
You restrict the power to reals and not general POPT. Okay.
Yes. So here what we're doing is either we restrict we extend the real quantum theory into a positive and pure tensor kind of theory. It's not exactly positive and pure tensor, but it within it.
I mean, also we have to take into account, like few other things. For example, there was a result by Manik Banik and others where they showed that, so when you try to, let's say, so you are taking, like your cone, like this cone of states and the cone of, like fx, and there are only certain compositions where, so you can take min tensor product, you can take max tensor product,
Yes.
but only in the case like this, the symmetry case is the case that you have you don't violate information causality. In other cases, what happens that if you compose in different way, then information causality may also get violated. I mean, which I think is another thing that one has to keep in mind when
that is true. I mean, these are very interesting aspects we haven't been studied into yet. All this GPT interpretation of what's going on. This is very interesting, and I'll be happy to think more about it. But we are not there yet. So yeah, this is interesting. Yeah, let's talk about it later. But right now, the only thing I can say is that the POPT theory was in any case very shaky, so we dropped it in favor of the symmetric theory. So basically, you just replace your Hilbert space from matrices to symmetric matrices, and you can show that it works if you change the tensor product. Also, you need to change a bit the Frobenius tensor product, the Frobenius inner product. We'll get back to it. And it's also the most interesting one because there is another group that actually found exactly the same results as us, but working in the pure state case. So Pedro Barriosita and his group in Düsseldorf. And we suspect it to be an example of the alternative predicted by this theoretical result by Erba and Perinotti, which tells that basically the composition rule is not the only one. So when they say composition rule here, they really mean tensor and Kronecker products. So we basically got scooped by Barriosita, so that's why our paper is such a mess right now. So we are about to publish, maybe cut the paper in two and publish a clarification of it soonish, by the end of the year, we hope. And I've been kind of lying about the previous slide. I put a little sneak on you, which is that it doesn't really work well. Like we are not sure if the R tensor product can really prove to be well defined as a tensor product on all symmetric matrices. We are still working the representation theory and stuff, but it's get very cumbersome. But what's important is that it always have a subspace we call special symmetric that is isomorphic to a complex quantum theory. So we can just restrict our symmetric R and Qt to the special symmetric one. And now it looks like a real quantum theory, just you have to assume the dimension are even, and you have to assume a new extra condition, like you're restricted in a subspace, which is you commute with some J matrix, and also use the different tensor product. But in this case, this is a representation of the tensor product, so you haven't changed this postulate. You only need to kind of change the validity of state postulate. So here, of course, people might object that, okay, I mean, you have proof in inverted comma the Renou et al. Result wrong by changing the postulates. Therefore, there is nothing new. Or they can also see, yeah, but you're just simulating complex quantum theory, whereas they are talking about a full-blown standalone theory of the real. And to this argument, we can say, Yes.
So sorry, Tim, I may have missed it. You may have explained it because I had to go for a minute. But what is J in the previous slide?
J, yes. So J, I haven't explained it yet, but this is just the matrix that represents the complex unit. So this,
right. Okay. Sorry, I forgot it. Thanks.
Its representation do not have to be the one we use, but it's just some matrix that when you square it is equal to minus the identity matrix, and you choose it. Yes, so you might then go for this objection, but then you can say, okay, but this is a purely scholastic argument, like we are changing postulate, but so they are. And also, like, other postulates to begin with, like the essence of quantum theory, is it really like these things defining quantum theory? And so now let's delve deeper into the choice of postulate. And the first thing we can notice, actually, is that there is something fishy in the first postulate, which is they say normalized vector, so normalized with respect to the inner product. But if you remember your quantum theory 101 courses, this is not exactly a quantum state. A quantum state in the pure state formalism has a phase freedom. Like any state is actually an equivalence class of all the states that are the same up to a phase. And what it means is that the vector are arrays. And this is actually the observation of the Barrios-Ita paper that I cited earlier, that Scooped. They start from there and say, yeah, but look, actually, like there is a internal symmetry of quantum states they are not taking into account. And what you can show is that there is two ways to take it into account. Either you take it literally, like you have a phase freedom, you take the corresponding notion of a phase freedom in the reals, which is a sign freedom, plus or minus. And this is equivalent to, say, your states of space, so basically think of it as the Bloch sphere, is actually like a geometrical kind of space, which is called a complex projective space. And now you change it into its real counterpart, a real projective space, if you do that. And this is equivalent, when you go to the mixed state representation, to requiring your Hermitian matrices to be equivalent to the symmetric matrices, and you obtain the theory of Renou et al. But this is a bit unsatisfactory because you've changed the intrinsic geometry of your objects. Like, is it even a quantum state anymore? And as I was saying, it's related to the Kronecker product of the real and Kronecker product of the complex having like different geometrical property. You can see it at the level of not Hilbert space, but when you see the cone, not the cone, it's actually a cone, yeah, sorry. The cone of projector on it, so the complex projective space, it has a very different geometry than the cone of real projector. Basically, one is an orientable manifold, for example, and the other is not. I mean, there is a lot of things I can go on around about, but just to say, you've changed the intrinsic geometry of quantum theory. Whereas if you do a more, it looks unnatural transformation, so you try to emulate the phase freedom into the reals. So here, again, using this J matrix and the identity matrix to emulate the decomposition of exponential into its complex and imaginary part, into its real and imaginary part. Then you obtain something else, which is you emulate the complex projective space, so your state space geometry is still the same. And this, when you go to the mixed state representation, requires your Hermitian matrices to be symmetric and to commute with J. So you exactly recover what we define as our real number quantum theory. So the idea is that now you have two alternatives to do the theory, which is basically based on an ambiguity in how you phrase the axiom. If you say this, instead of being a vector, it should be a ray, then you have an ambiguity, and you can choose between the Renou et al. Theory and our theory. So, but this was known, sorry. Like I cited this paper of Dyson, which is very, very theoretical, but if you read it in details, he actually predicted all these issues. Like he basically told you, like, if you want to do complex quantum theory, the representation on the Hilbert space have several ways of doing so. He was talking a lot about super selection rule, but what he was saying is that if you want the genuine out-of-the-book quantum theory, you should always have an intrinsic complex structure. So some matrix that behave like if you had a complex number in your theory. So some matrix J, even though you are formulating your theory over the quaternion, the p-adic numbers, or whatever. And so what Renou et al. Did is just to remove this implicit postulate or structure, which correspond to the phase freedom, and we did not, and that's how we end up with two different theories. Okay, so now you might think, well, this is two interesting theories, but there is still something weird, which is we obey the same postulates, we just have some weird notion of how do we encode the phase in our works. But then how can we have opposite conclusion? How can our theory, which is actually more restricted than the Renou et al. Theory, is able to emulate all the prediction of complex quantum theory, whereas theirs has differences. And so that's what we will look into the last part of this talk. And this is upcoming work, by the way. And so now we need once again to go back to the postulates. So we've seen that here vector should be replaced by arrays. There is also something else that must be seen in the postulates. When you see how the composition postulate is phrased, so you have tensor product of Hilbert space. This is kind of standard. Then operation on Bob's side should be independent of operation on Alice's side. This is quite standard. But then the last sentence, the state representing two independent preparation of the two system is the tensor product of the two preparation. It looks very intuitive, like this is what you do when you're computing. This is fine. But actually it's not very standard. Like when you look at most textbooks and stuff, they never assume this property. They just say, derive it in the best books, or just say, okay, it must be like that because some notion or something, or sometimes they don't justify it, but they never take it as a postulate. And so we started wondering, why is it non-standard? And actually this composition postulates as therefore two independent parts, which are based on different heuristics. That's why it's non-standard to add the last sentence. The first heuristic is basically you want all the operation you do on Alice's side to commute with all the operation you do on Bob's side. This is like the commuting paradigm, if I may use this word. And this is usually how you define, especially in algebraic quantum field theory and more complicated theories, local parties. Whereas saying that two states should be in tensor product is derived from this first property by saying my commuting operations, so the one that I know are independent of each other, whatever they do, they should always lead to independent distribution. And if this is the case, then you can prove that this is a tensor product state. But this becomes important. So the first thing, the first postulate, the first heuristic behind the postulate, you can prove that it's just saying, okay, if Alice is acting with operator E and Bob is acting with operator F, and they act globally, if they are trivially acting on each other, so independent of each other, the operation should always commute. And this is equivalent to saying, okay, we can find a representation in which they are in pure tensor product. This is the Tserelson conjecture, and you know it's always true for the dimension being finite. Of course, there is big issues that happen with finite dimension, but this is not our concern here. Just to say, you can use this postulate one, this first part of the postulate 4. But the second part,
yes? You're going to pass. So the point, I thought the whole point was that we're not putting any constraints on the dimension. So how do you so easily, discount the dimensional case?
I pulled another sneaky on you is that we don't care about the dimension as long as it's countable and kind of finite. Like you don't go into Tserelson problem because otherwise you have a way more complicated problem than all this real quantum theory mumbo jumbo, which is Tserelson conjecture, which, if you go to infinite dimension already, you have different statistics just because we know the Tserelson conjecture to be false. So indeed, we had implicitly, I assume the dimension to be always finite.
I see. Okay.
But I mean, it can go to infinity, but in a countable manner, and it will still hold. Maybe you can generalize the result to the infinite case, but then you need to start doing like type 3 von Neumann algebra and this horrible mathematical thing, and I have not paid enough for that.
Thanks.
You're welcome. And then I was saying, so the second part, so this first part is totally acceptable by this kind of heuristic I just said. And it does not depend in particular of the field or whatever you're doing. The second part starts to depend on the field. So what you say is that if you have two local operators, so assuming one, you can represent them as tensor product, and so Alice is measuring A given X, and Bob is measuring B given Y. And so if you assume that independent sources lead to independent distribution, so if these guys, whatever they measure, always obtain independent sources, independent distribution, sorry, this define an independent source, then you should be able to prove this thing to be equivalent to being in a pure tensor product, which is true for the R tensor product and the complex tensor product, but it's not true for the Kronecker product of the reals. It's only a sufficient condition. This is exactly non-local tomography coming back into the scene. And so to see it, let's see an example. What this thing means is that there are states representing the state of two independent sources that are not in a pure Kronecker product form, but they will be in a pure R tensor product form. So for example, the state we used earlier, this one is a real matrix. It has independent statistics. These are the argument I've said earlier. But over R, it's not pure states. It's not even a pure state over C. If you use the Kronecker product, it's separable. But now, if you consider it using the other tensor product, the R tensor product, well, consider these states, which is just the mixed, the maximally mixed states, tensor, the maximally mixed state. So, you know, it's really independent and a pure product, tensor product state. If now you represent it in terms of the Kronecker product, you quickly compute that this is exactly the state I just mentioned. So basically this one, you know that it is a pure tensor product using this representation, but it's not pure tensor products at all. It's actually entangled if you use the Kronecker product. And so if you say, I must use the Kronecker product, but I must only use pure tensor products of Kronecker product to represent sources, independent sources, you basically have put a hidden assumption in your theory, which is to say that basically you forbid certain preparation that if you were to use a different theory, you could interpret them as a local preparation. So basically, you've removed preparation from the set of possible preparation. And so we believe that's why there is a discrepancy in statistics. They have a hidden model-dependent assumption that removes certain preparations. And therefore, because of that, yes?
Can I ask a question?
Yeah.
So is it clear what step of the proof goes wrong in the proof being that for complex fields it is equivalent whether you take a tensor product or have independent sources? Is it like clear? Is it like a dimension counting argument that goes wrong?
It's not even a dimension counting argument. Is so
this is a counter example, I guess, that you're showing, but the proof itself must break at some point, right? Is it simple enough to spot it, or?
So where do you spot it? So the this way, sorry, from the pure tensor to the factoring distribution is trivial because basically you have a pure tensor on each side, and then you can just do the you can factor. So this way is trivial. It's the other way to go around. And like in the proof, it just breaks by finding a state like this. This is a state that will lead to a factoring probability distribution, but is not of this form. So, I mean, this is a
example. It's a bit out. I'll think about it. I don't even know the proof for the complex case, so I should look at that. So thank you. Carry on.
Yeah, indeed. I tried to find a proof actually, and this is not a well-known proof. There is in the work of Arthur Fine, when they were talking a lot about the Bell states, some sketch of proof. There is some in the work of Bell, but I couldn't find a cool proof. But then again, it's kind of easy. You can, I mean, easy-ish. Over the complex, you can use basis decomposition, I think, and then some, well, things related to Schmidt decomposition. Yeah, I don't have a clear idea of the proof of the complex right now in my mind, but I mean, you can prove it. That's all I can say, like right now, out of my hat, on top of my head. Yes, so all this to say, yes, these two things are different, and this induce a model-dependent hypothesis in the theory. So now what we want to say is that if you have this choice of postulates, well, we can change the vector word into ray, and we can change the last part of the postulates to is the tensor product into leads to independent measurement outcomes. I believe you can agree these are two sensible modifications that most books will agree with, depending on the books. Like Nielsen and Schwang will be more like this is tensor product and this is vector, but other books will say it's rays, like the Griffiths, for example, and independent measurement outcomes. So it's kind of wording issues. And the thing is, if you do these changes to be a bit more, I don't know, operational or rigorous, or I don't know how to call it, then the result of Renou et al. Is no longer true, because if you do these two changes, you can use the real number quantum theory, which is described, and therefore you can show that every experimental prediction over the complex can be made over the reals. So all this very long thing to say that the paper is nice. It's a nice mathematical statement, like proving the difference in these two prediction models, and there was nice STPs and stuff. I liked it, but the problem is we show that this result is purely a mathematical result, because on the first hand, on the one hand, it has a representation dependency. So the fact that you must assume you're in the real quantum theory and not in the real number quantum theory alternative we showed. And also it has some kind of model-dependent hypothesis. So the fact that you must assume independent sources to always be in a pure tensor product state, which, I mean, this is a mathematical hypothesis. If you want to justify an experiment on top of it, it becomes kind of messy, right? And that's basically all I had to say. Thanks a lot for your attention and your questions.